Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we are going to introduce Matlab. So in this topic, we will introduce Matlab and the idea of interpreters and interpreted languages. We will discuss arithmetic operations and how they are performed in Matlab. We will look at complex numbers. We will describe vectors, vector operations, and functions on vectors. And then we will look at matrices, matrix operations, and functions on matrices. In your Fundamentals of Computation course, you are using C++. C++ is a compiled language. You author the program. You compile the code into machine instructions. You execute the file, the executable, containing those instructions. The instructions perform the statements you coded, which hopefully are what you meant to be coded. An error in the code or design means you must fix the issue, recompile, and re-execute the program. Java, C, C++, C#, and many other languages are compiled. And there are benefits to this. On the other hand, Matlab, Octave, and Python are interpreted languages. You enter one statement at a time at the prompt. That statement is then interpreted, and appropriate functions are called to make that statement perform what you wanted it to do. One thing that's interesting is you can make mistakes. So if you have a syntax error in one statement, it does not undo any of the previous statements that you have already executed. Therefore, it's actually very useful for modeling. Now, Octave is a free version of Matlab, and for all intents and purposes in this course, it is equivalent to Matlab. So you can use one or the other. There are subtle differences in languages, and they are diverging a little bit more now, but for the most part, from their linear algebra point of view, they are equivalent. So whenever in any of the talks in this course we refer to Matlab, this means Matlab or Octave. To begin, in Matlab, you can execute statements one at a time. So for example, if you launch Matlab, at the command window, you will see a prompt. And at this prompt, you can now start typing elementary mathematics. As soon as you get to the end of the line, you hit enter, and it performs that calculation. Now, by default, all calculations in Matlab are performed using double precision floating point numbers, even the ones that appear to be integer calculations. The displayed result is, however, restricted to only a few digits. So, for example, if you were to calculate 3.2 divided by 7.8, we would see 0.41026, or something close to that, depending on which version or variation you are executing. Now, to view all 16 decimal digits of precision, use format long. So this command tells the interpreter to display all floating point numbers using 16 significant digits, which is approximately how many digits 53 significant bits represent. So now, if we perform such a calculation, we get all digits. Now, This, of course, does lead to a lot of information being displayed to the screen, so you can always return to the default display as follows. Just type format, and now we're back to normal. One nice feature is that it's easy to view the double precision floating point format in binary, well, as represented using hexadecimal numbers, using format hex. So at the prompt, type format hex and perform your calculation. So now we see a string of 16 hexadecimal digits representing 64 bits. In this case, if you substitute each of the hexadecimal digits for their corresponding 4-bit representation, we get that this number represents a leading 0 bit, indicating it is a positive result. The balance of the first hexadecimal digit together with the second and third represent the exponent, and in this case you can see that the exponent is 2 less than the bias, and subsequently we see the bits of the mantissa. So consequently this represents the following number, where we have the implied leading 1, please remember that, followed by the mantissa, all times 2 to the negative 2. In Matlab, the arithmetic operations are similar to that in C++. Plus, minus, the asterisk, and the forward slash. Additionally, the caret represents exponentiation and not XOR. C was written as a programming language for operating systems, and caret was appropriately used for XOR. You don't necessarily use exponentiation that often in an operating system, and besides, if you wanted to perform exponentiation, you simply call an appropriate function. So now, returning from format hex to our regular format, we just type format, and now we can calculate 1.3 to the exponent 4.7. And this happens to equal 3.4319. In Matlab, just like C, assignment occurs with the assignment operator, which is represented with the equal character. However, it's not always required. In fact, you may have always noticed that the answer was always in the form ants equals whatever the result was. What's interesting in Matlab is that if you do not assign the result of a statement to a variable, that result is automatically assigned to the variable ants, of course for answer. You may continue to work with the variable ants just like any other variable. But again, with each subsequent statement you enter is assigned a new value. So it, of course, only holds the most recent value assigned to it. So if we start with 3.2 plus 5.7, ants is assigned 8.9. If we now calculate ants squared minus 0.3, we get ants being assigned the value 78.91, and we can now continue to use this result. Of course, it's much easier in many cases to just assign results to another variable, and the variable names in Matlab have the same naming convention as in C++. The first character is a letter or an underscore, and all subsequent characters, if any, may be letters, digits, or underscores. One point. ANTS continues to be assigned the most recent value it was assigned to until you perform another calculation that does not assign the result to an actual variable. As an example of assigning to variables, let us assign x the value 3.2. Then assign y the value of x cubed minus 4.9x squared plus 1.7x minus 8.3. Now we get that y is equal to negative 20.468, perhaps with a few more digits that are not being displayed to the screen. Now, that first statement is something quite useful. If you place a semicolon at the end of a statement, the statement is still executed. So x is assigned the value 3.2. However, the output is suppressed. Also, the semicolon allows you to place multiple statements onto a single line, but in general, this isn't probably that great an idea from the point of view of readability and maintenance. Now, if we wanted to use complex numbers in C++, this requires the complex class, which appears in the standard complex library. So we have our function declarations and our function definitions, and we have a few statements that declare Z and J to be complex numbers. Complex is a templated type, so you specify what you want the complex numbers to store. Is it a pair of doubles? Is it a pair of float? Or perhaps some other approximation of real numbers? In this case, Z and J store two doubles, one double storing the real component, another double storing the imaginary component. So we've initialized Z, and then we perform statements such as Z plus equals negative 1.5 plus 2.2 times J. Notice that J has been declared to be a complex number, and therefore all of this works out, and the output, when displayed to the screen, is written as a pair of numbers, the first assumed to be the real component and the second to be the imaginary component. In Matlab, however, complex numbers are integrated into the design. So I can assign to Z 0.5 minus 0.7 J. Unfortunately, the output is always going to be I. You can't change this in any way. However, you are allowed to use J in your input. We can now calculate Z squared plus 1, and it will square this complex number and add to it the real value 1. So in this case, we have this result. Now, if we calculate Z to the 1000, well, let's see. Z is that number there. Its absolute value is the square root of 0.25 plus 0.49, which is a value less than 1 when we add them together, and the square root of something that's less than 1 is still less than 1. So from secondary school, you may remember that if you raise a number that has an absolute value less than 1, and you raise that number to a large value, the magnitude of that number shrinks. Well, in this case, if we take this particular z and raise it to the power 100, we get a very small number indeed, on the order of, well, as you can see, 8.8 times 10 to the negative 67 minus 4.03 times 10 to the negative 61j. Also in Matlab, all mathematical functions are ready to take both real and complex arguments. So here x is being assigned 8.2, z is being assigned 0.5 minus 0.7j. We can calculate cosine of x, which is approximately this value, but we can also calculate sine of z, which is approximately this value. Remember that sine of z is approximately equal to z for small values of z, and you can sort of see that here. You'll recall the formula that tan squared plus 1 is equal to sec squared. Consequently, if you calculate tan squared plus 1 minus sec squared for a particular x, that should equal 0. Well, it doesn't, because after all, we have floating point errors to contend with. However, as we can see, it's not exactly 0, but it is a very small number. It's actually approximately on the order of 2 to the negative 52, which is the number of bits in the mantissa. You may remember from secondary school that sec squared plus cosecant squared is equal to tan plus cotan all squared. So consequently, whether or not you have a real value or a complex value, this should be true. And calculating this, yes, we do see that this is true. After all, the result is a very small number minus another small number times j. Now, one warning in Matlab, more or less everything other than a few keywords is assignable. So here I am assigning z a complex value. Okay. However, what happens if I assign j the value of 2? Okay, so now j is assigned something. Suppose instead I now try to assign z the value of 0.5 minus 0.7, not j, but times j. Well, guess what? J is now 2, so this is probably not going to give you the result you were expecting. Similarly, if you were to calculate this, instead of getting what you thought you were getting, 0.5 minus j, it would actually evaluate to negative 1.5. And unfortunately, j ends up being used very often as the index to a for loop. After all, in Matlab, very often you do have matrices, and it's far too common to use the indices I and j. Consequently, you should never multiply by j, but instead always use a number with the j juxtaposed. That includes using 1j to represent what you would normally just think of as j. It's just easier. So even though j is assigned, now z is assigned 0.5 minus j. Here is a list of some of the mathematical functions available by default when you launch Matlab. In the right-hand column, we have the exponential function e to the x, and of course x can be real or complex. Log of x returns the natural logarithm, while log 10 returns log base 10, or the common logarithm. We also have log 2 and the square root function, as well as the hypotenuse function, which takes two arguments and calculates the square root of the sum of the squares of those entries. Now here is an interesting function that you may not have seen before. This calculates the natural logarithm of 1 plus x. Now why is that necessary? Well, you may recall previously we've described the fact that x plus y can still equal x even if y is non-zero. Consequently, there must be small values of x such that 1 plus x is equal to 1 or very close to 1 with significant loss of precision with respect to the digits of x. This function allows you to calculate the natural logarithm of 1 plus x without actually passing it 1 plus x, and this is going to be much more accurate for calculating log of 1 plus x for very small values of x. So for example, here we have a very small number, 1.3 times 10 to the negative 14. We're going to use format long. Now, if I simply calculate the natural logarithm of 1 plus x, I get this result here. If I calculate log of 1 plus x, I get a significantly different answer. And in fact, this second answer is correct to all 16 significant digits. You can check this using any language that allows you to have arbitrary precision floating point computations. However, here we are restricted to just using double. The relative error of our first calculation is actually quite large. It's almost 0.01% relative error, which isn't very good when compared to essentially something that gave us 16 significant digits. The reason is when we calculated 1 plus x, we lost all but the first two digits of x because we could only store the result to 16 significant digits. Well, technically 53 significant bits. There are also numerous functions in Matlab for querying complex numbers. Here are some examples. The absolute value and the angle of z, the conjugate of z, is real. This is a query that returns 0 or 1 depending on whether or not z is not real or real respectively. That is, it's real if its imaginary component is 0. Then we can also extract the real and imaginary components. Here are some examples. Let's first by defining z. There we go. We can now see that z is equal to the real part of z plus the imaginary part of z times j. Again, we should always use 1j. And of course, those two are equal. Now you may recall the polar representation. Every single complex number is equal to its absolute value times e to the j times the argument or angle of z. And of course the angle must be in radians. As you can see here, we can try this out, and yes, indeed, it appears to be pretty close. It's not exactly correct, as the first number is actually off in the last 2 or 3 bits, and the second or imaginary component is off in the last bit. However, that's okay. It's close enough. It's about 50 significant bits of precision. We can also calculate the conjugate of z, which simply negates the imaginary part of the complex number. You can see a full list of functions at the following page at the MathWorks website. MathWorks is the company that produces Matlab. Now, if you want to see the help page for any function, or even some of the operations, all you have to do is at the prompt type help followed by the function name. This will print out the corresponding help page. However, there's one thing that's interesting here. You can also call, instead of help sign, you can type doc sign. And if you are using a GUI version of Matlab, this will open up the document page for the sign function, which is a little bit more detailed than the built-in text version. To enter a vector in Matlab, after all, Matlab actually stands for Matrix Laboratory, all we do is we provide Matlab with a list of values surrounded by square brackets. So here U is assigned a vector containing 4 entries, and this will be a row vector. All right, not a problem. As you may have guessed, like the double slash in C++, the percent character starts a comment to the end of the line. If you wanted to create a column vector, one way to do so is to create a row vector and then take its conjugate. Well, the tick mark is actually the conjugate transpose, but at least for a real vector, this simply converts the row vector into a column vector. And actually, it's a lot easier to read numbers relative to each other when they are represented as a column. In fact, most of your matrices will be most of your vectors will be columns. When defining a vector, commas are actually optional, so you could include them if you wanted to. So we get exactly the same result as before. If you wanted to separate rows, you could also use the semicolon instead. So here we have a column vector with 4 entries, and each entry on a separate row is separated by a semicolon. This is a little bit more awkward to type. The only issue is that if you have a complex vector, you have to look at using the transpose and not the default conjugate transpose. But that will be a topic for later. So here, again, we get exactly what we were expecting. Now, the first useful feature in Matlab, if you have a mathematical or complex function and you pass it an argument that is a vector, that function is then applied to each entry of that vector. So here's a vector with 4 entries. I calculate sine of u, and this applies the sine function to each of the 4 entries. Of course, the result is a new vector. The vector u has not changed. Here I have a column vector with two complex entries. If I call angle on each of these, I get the angle of each of the arguments. So angle is applied to each of the entries of this two-dimensional column vector, resulting in a two-dimensional real vector, as the angle is a real number. Now, in linear algebra, you will remember that the vector space operations were vector addition and scalar multiplication. Well, these work as expected in Matlab. So here I have assigned U a four-dimensional column vector, and here V is also assigned a four-dimensional column vector. The dimensions must agree, as must their orientation, which is why you should always be using column vectors anyway. So if we now calculate the linear combination of the vectors u and v, 0.7u minus 3.6v, Matlab happily calculates this result for us. In Matlab, you can access and or assign to individual entries of a vector by using parentheses to indicate which entry you're interested in. Now, it's important to remember that the indices go from 1 to the dimension of the vector, unlike C++, where it goes from 0 to capacity minus 1. So Matlab uses the linear algebra paradigm for indexing, not the C++ variation. So here we have a four-dimensional column vector. It doesn't matter if it's a column vector or a row vector, you access the entries the same way. And I can access what is at index 1. And I get back exactly what is at that index, 4.5. However, I can also assign to the second index of the vector. Now, generally, it's a good idea to put a semicolon after this statement, for Matlab actually prints out the entire vector again. After all, now the vector has changed, and as you can see, the second entry is no longer negative 2.7, it is now 17.6. Now, just in case you forget and you try to index the entries of a vector with square brackets and not round parentheses, that is, you were using C++ until recently, fortunately the error message is quite clear and it explicitly tells you to use parentheses. All right, that's nice. Now, as we've already stated, most mathematical functions map onto the individual entries of the vector. Consequently, given this vector, the absolute value of this vector is simply the absolute value of each of the entries of that vector. On the other hand, some functions work on the entire vector. So, for example, here's our vector u. We can ask, what is the norm of u? Now, this is what you may have called the Euclidean norm, or the 2 norm, or perhaps the length of the vector. In any case, this calculates the square root of the sum of the squares of the entries. So, consequently, the 2 norm of this vector is 10.413. Now, the 1 norm, which has similar properties to the 2 norm, is defined as the sum of the absolute values of the entries. All right, so looking at this, we've got about 8, 9, 10, 11, 12, 13, 14, 15, 16, 17.4. So this should be about 17.4, yes. Okay, that's another way of measuring the length of a vector. The infinity norm is defined as the entry that is largest in absolute value. So in this case, that is just 8.9. Okay. You can also find the dimension of a vector with the length function. So here we have a four-dimensional vector, and length actually returns exactly that value. To enter a matrix instead of a vector, you just have to provide Matlab with a list of values, row by row, with the rows separated by either a semicolon or enter, or if you really want, both. So, for example, here you will see that I have three sets of three values separated by semicolons. So this will create a square 3 by 3 matrix. Next, here I have a rectangular 3 by 4 matrix. And again, hitting enter, I get exactly that printed to the screen. So here at the end of every row, I simply hit enter and carry on. Now, I hit a few spaces here to line things up, but you don't have to. You can just carry on at the start of the next line. Now, the arithmetic of matrices is similar to that of vectors. So, for example, with the plus operator, you can add two matrices that have the same dimension. And of course, the sum will have the same dimension as both of those operands. You can multiply a matrix by a scalar, and the dimension remains unchanged. This simply multiplies each entry of the matrix by that particular scalar. You can multiply two matrices if the column dimension of the first equals the row dimension of the second. And this is going to produce a matrix that has the row dimension of the first and the column dimension of the second. This was, of course, defined in your linear algebra course. You can also raise a square matrix to an integer exponent. All right, so just as one very quick example, from the previous page, we defined A to be a 3 by 3 square matrix. So we can multiply that matrix by itself 3 times, and the result will still be a 3 by 3 matrix. So we can calculate A cubed. Onto that, we can calculate A squared, multiply the matrix by itself, and then multiply each entry by 2.5. And finally, we can multiply each entry of the matrix A by the scalar 0.5. We can add all of these together, and we get the following. Now, this is a way that Matlab simplifies the output when the entries of a matrix are large. So as you can see, we have a 3 by 3 matrix, but right above it, we have 1.0 times 10 to the 3. So the actual matrix is the matrix we see below with each entry multiplied by 1,000. Or in other words, each entry has the decimal point moved 3 places to the right. This scalar multiple will only ever be a power of 10, so that you can still look at the entries of the matrix, and all you have to do is shift the decimal point appropriately. You can also multiply a matrix and a column vector. Now, the column dimension of the matrix must equal the dimension of the vector. So you'll recall that B was a 3 by 4 matrix and U was a 4-dimensional matrix. Therefore, multiplying these two will give a 3-dimensional vector. And that's what we get. Notice that the result is assigned to ants. You'll recall now that the matrix A was 3 by 3, and this is a 3-dimensional vector. Consequently, multiplying this result by ants gives us the vector we see here. Now, as with vectors, there are functions that also work on the entire matrix, and what is returned depends on what's requested. For example, recall that the matrix A was square and 3 by 3. We can therefore ask what is the change in ratio of volumes as we map a region under this matrix A. Well, that's the determinant, and in this case, the determinant is 413.96. We can ask what is the trace of this matrix, which is the sum of the entries on the diagonal, 22.7. We can even ask what are the eigenvalues of that matrix, and Matlab will happily calculate them for you. We can also ask for something slightly different. Eigenvalues are really only useful for symmetric real matrices. For non-symmetric real matrices, we have the SVD, or the singular value decomposition. In that case, you can see that the singular values are similar to but subtly different from the eigenvalues. Now, in each of these cases, we did not assign the result to anything, and therefore the result was assigned to the variable ants. And so in the first two, ants was assigned a scalar, while in the second two, ants was assigned a column vector. Now in C++, a function only has one return value, and previously we saw that if we called eig, it just returned a single vector. In fact, if you assigned the output of eig to a single variable, that variable would be assigned a vector of the, in this case, 3 eigenvalues. However, now we have something different. We are assigning the output of eig not to one value or one variable, but to a row vector of 2 different variables. This is something very interesting and peculiar to Matlab. The function can actually know how many return variables are being asked for, and then tailor the output based on the number of return variables there are. So if you were to call eig with 2 return variables, the first is assigned a matrix of 3 eigenvectors, and the second is assigned a diagonal matrix with the corresponding eigenvalues on the diagonal. So the first column of E is an eigenvector corresponding to the eigenvalue 9.3449, and so on and so forth for the other 2 eigenvalues and corresponding eigenvectors. Now, you may recall diagonalization. So if we calculate the eigenvalue matrix times the diagonal matrix times the inverse of the eigenvalue matrix, we get the original matrix back, at least up to the point that we are going to introduce small errors because we are performing arithmetic operations with floating point numbers. Now, if the matrix A was symmetric, then E could be an orthogonal matrix, in which case its inverse is the transpose. However, in this case, that is not the case. You may recall that the matrix A was not symmetric, and therefore the inverse must be explicitly calculated. So one major question in linear algebra is solving systems of linear equations. For example, if A maps a vector space U onto a vector space V, and V, the vector, is one such vector in the codomain, find a vector U in the domain such that A times U is equal to that target vector V. So here is my 3 by 3 matrix, and of course this matrix A maps R3 into R3. Here is a target vector. So we would like to find a vector U such that A times U is equal to this vector V. Now, you'll recall from a previous slide that the determinant was definitely not 0, and consequently A must be invertible, and therefore a unique solution must exist. Well, we can calculate that solution by using the backslash operator. So A backslash V will perform Gaussian elimination and backward substitution in such a way as to minimize the error of the answer as much as possible with algorithms beyond the scope of even this course, and we get that the vector U that maps onto V under the matrix A is this vector here. Well, at least to 4 significant digits. Of course, 16 significant digits are stored in the double precision floating point representation. We can check this by multiplying this vector U by A. All right, let's see what the result is. Well, it looks pretty close to the vector 5, negative 4, 6, which is what we designated the target vector as. But we're printing a lot of zeros, and that hints that these are not exact. Well, we can use format hex and recalculate A times U. And suddenly we see that, oh, wait a second, the first value is indeed the floating point representation of 5. The next is the floating point representation of negative 4. You'll note that 4 plus 8 is C, meaning that we set the sign bit to 1. However, looking at the last one, 6, that's not 6. It's ever so slightly less than 6. Basically, it's correct to all bits except the last. So that's actually pretty good, given that we have performed Gaussian elimination and backward substitution, and now we are multiplying the resulting vector u by the matrix A. Now, the last topic we're going to look at will be accessing and assigning to entries of a matrix. Accessing is reasonably straightforward. Here is our 3 by 3 matrix A. We can access the second third entry, that is second row, third column, and that is the value 0.4. However, Matlab is more powerful than that. Here, I replace the second entry with a colon. What this says is give me every entry in the second row. Well, every entry in the second row is 0.2, 6.4, 0.4. Similarly, we can extract entire column vectors of the matrix. So here we ask for all entries in the third column. And that would, of course, be the entries negative 0.3, 0.4, 9.2. That's a nice feature. Imagine trying to do that in C++. We can also assign to the individual entries of a matrix. So if you forget what a matrix looks like, you can actually just type the name of the matrix at the prompt and hit enter. So this is the matrix B we entered a few slides back. Well, we can now assign entry 1, 4 of that matrix to be equal to 1. Remember, the indices go from 1 to the corresponding dimension and not 0 to the corresponding dimension minus 1. So now the top right entry of the matrix is assigned the value 1. We can even assign to entire rows of a matrix. This will be fun. But before we do that, let us consider solving the system of linear equations by finding a vector u such that a times u is equal to a target vector v. What did you do? Well, the first thing you did is you created an augmented matrix. Now, I have a variable AV here, and I'm assigning to it, well, square brackets, so it looks like I'm creating a row vector or a matrix, but the first entry is a 3 by 3 matrix, and the second entry is a three-dimensional column vector. What this does is it creates the augmented matrix where the first 3 columns are the matrix A and the last column is the vector V. Now, what did you do here when you were performing Gaussian elimination? Well, the first step you did was eliminated all non-zero entries below 7.1. So the first thing you did is you added negative 0.2 times negative 2 divided by 7.1 all times the first row added onto the second row. Well, we can actually do that here. So onto the second row, we are assigning the value of the second row of the matrix minus the ratio of the entry 0.2 divided by 7.1 all times the first row. Now, the first row is a 4-dimensional row vector. the second row is a four-dimensional row vector, so this is just the second row times plus a scalar times the first row. And whatever this calculates to will be assigned to the second row. Okay, we just did part of your final examination from 1A. What's next? Well, we have to get rid of negative 0.4. Well, we perform the exact same operation, except now we replace the third row with an appropriate multiple of the first row added onto the third row. And that now eliminates both of those entries below the diagonal entry 7.1. Carrying on, we now have to add an appropriate multiple of the second row onto the third row. Now the augmented matrix is in row echelon form, and we can perform Gaussian backward substitution to find the solution. Now I'm going to print out the solution using all 16 significant digits, and so the third entry in the solution can be found by dividing 6.8187 by 9.1301. But of course, Matlab will do the work for us. And there is our answer. Now, I'm not going to do all of the backward substitution, but if we just calculate the solution using the backslash operator, we do see that the last entry matches what we found to all significant digits. That's important, but the matrix we were looking at was also sort of special, because you may have noticed that all of the entries on the diagonal were significantly larger than all off-diagonal entries. Now question. How do we swap two rows? After all, there are three elementary row operations. Adding a scalar multiple of one row onto another, which we've just done. Multiplying one row in a matrix by a scalar that is non-zero. Well, we haven't done that, but you can probably figure that one out. But the last elementary row operation is swapping two rows. Well, let's review. Here is the matrix B. Suppose that we, rather than extracting the first or third rows, let us extract the third row and then the first row. So that's exactly what happens here. So as you can see, the first row of this result is the third row of B, whereas the second row of the result is the first row of B. Well, this gives us some hope. So in fact, if you assign to the first and third rows of the matrix B the third and first rows of the matrix B, you've swapped those two rows. Much more convenient than trying to do this in C++. So following this topic, you now understand arithmetic operations for both real and complex numbers as implemented in Matlab, using, of course, the double precision floating point representation. You are aware of functions on real and complex numbers, and hopefully you've had a very quick review of complex numbers. You also know how to create a vector and understand that vector operations are also defined in Matlab, as well as various functions defined on vectors, such as the norm, and length. You know how to create a matrix, and you understand that matrix operations are also defined. And finally, you now know how to solve a system of linear equations in Matlab, and you have done so in two ways, one by using the backslash operator and the other by implementing by hand Gaussian elimination and backward substitution. However, even then, it's much easier than it was in your final examination for your course on linear algebra. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!